One of the biggest mysteries in modern physics is the nature of dark matter, the invisible substance that makes up most of the mass in the universe. Scientists have been searching for clues about what dark matter is and how it behaves for decades, but so far they have not found any direct evidence of its existence. Instead, they have inferred its presence from its gravitational effects on normal matter such as stars and galaxies. However, not everyone agrees that dark matter is real. Some alternative theories propose that there is no need for dark matter and that the observed phenomena can be explained by modifying the laws of physics or gravity. These theories claim that dark matter is a fiction and that we need to rethink our understanding of the universe. But how can we settle this debate once and for all? Is there a way to test whether dark matter is real or not? Well, there is a new space telescope that might be able to do just that. It is called Euclid, and it has just opened its eyes for the first time. Euclid is designed to study the dark universe in unprecedented detail and accuracy by mapping the distribution and evolution of dark matter and dark energy over cosmic history. By doing so, Euclid will help us test whether our current theories of physics and gravity are correct, or whether we need to revise them. In this video, we will explore how Euclid works, what it has seen so far, and what it hopes to discover in the future. If you want to learn more about Euclid and how it will collaborate with the James Webb Space Telescope, you can watch our previous episode. But for now, let's dive into the dark side of the universe with Euclid. Euclid is a European Space Agency mission that was launched on July 1, 2023, and it is designed to study the dark universe, which is composed of dark matter and dark energy. These are mysterious substances that make up about 95% of the total mass and energy of the universe, but we don't know what they are or how they work. Dark matter is an invisible form of matter that holds galaxies and clusters together with its gravity. On the other hand, dark energy is a mysterious force that causes the expansion of the universe to accelerate over time. By studying these phenomena, Euclid hopes to shed light on some of the biggest questions in cosmology, such as the origin, evolution, and fate of the universe. To do this, Euclid has two powerful cameras on board, a visible imager, VIS, and a near-infrared spectrometer and photometer, NISP. These cameras can capture images of billions of galaxies across more than a third of the sky, spanning a distance of 10 billion light-years. That means they can see how the universe looked when it was only a few billion years old. By measuring the shapes, positions, colors, and distances of these galaxies, Euclid can map the distribution and evolution of dark matter and dark energy over cosmic history. But how do these cameras work? Well, they use different types of detectors to capture different wavelengths of light. The VIS camera uses CCDs, charge-coupled devices, to record visible light, which is the same kind of technology used in digital cameras and smartphones. The NISP camera uses H2RGs, Hawaii 2RGs, to record near-infrared light, which is a type of light that is invisible to our eyes but can penetrate dust and gas in space. The NISP camera also has a special feature. It can split the light into its spectrum using a grism, a combination of a prism and a grating. This allows it to measure the redshift of galaxies, which is a measure of how much their light has been stretched by the expansion of the universe. By knowing the redshift, we can estimate how far away a galaxy is and how fast it is moving away from us. These cameras have many advantages over other space telescopes. For example, they have a very large field of view, which means they can cover a larger area of the sky in less time. They also have a very high resolution, which means they can see more details and fainter objects. And they have a very wide wavelength range, which means they can see more types of galaxies and stars. However, these cameras also face some challenges. For example, they have to deal with very high radiation levels in space, which can damage their detectors and electronics. They also have to cope with very low temperatures, which can affect their performance and stability. And they have to calibrate their images very carefully, which means they have to correct for any distortions or errors caused by their optics or environment. To overcome these challenges, Euclid's cameras were tested and calibrated before and after launch using various methods and instruments. Before launch, they were subjected to rigorous simulations and experiments on Earth to ensure their quality and accuracy. For example, they were placed in vacuum chambers that mimic the conditions in space. They were also exposed to different sources of light that simulated the stars and galaxies they would observe, and they were calibrated using special devices that measured their sensitivity, alignment, focus, distortion, noise, and other parameters. After launch, they were also tested and calibrated using real observations from space. For example, they took images of well-known stars and galaxies that served as reference points for their measurements. They also took images of empty regions of the sky that served as backgrounds for their subtraction, and they took images with different exposure times and filters that served as inputs for their analysis. Some of the difficulties they encountered during these tests and calibrations were related to the complexity and variability of their instruments. For example, they had to account for the effects of temperature changes on their detectors and optics. They also had to correct for any shifts or drifts in their pointing or focus due to vibrations or thermal expansion, and they had to remove any stray light or cosmic rays that could contaminate their images. Some of the successes they achieved during these tests and calibrations were related to the performance and reliability of their instruments. For example, they confirmed that their detectors and optics were working as expected and within their specifications. They also verified that their images were sharp and clear and matched their simulations and predictions. And they demonstrated that their cameras were ready and capable of fulfilling their scientific goals. After these tests and calibrations, Euclid's cameras were able to take their first sample pictures from space. These pictures were released to the public on July 28, 2023, and they showed some amazing views of the stars and galaxies in the universe. Let's take a look at some of them and see what they reveal. The first picture we see is from the VIS camera, and it shows a patch of sky that contains about 100,000 stars and galaxies. The colors in this picture represent different levels of brightness, with blue being the brightest and red being the faintest. The resolution of this picture is about 0.1 arcseconds, which means it can separate objects that are as close as 0.1 seconds of arc, or about 500 meters, at a distance of 10 billion light-years. This picture is remarkable because it shows the power and precision of the VIS camera. It can capture images that are much deeper and sharper than those taken by previous or current space telescopes, such as Hubble or James Webb. For comparison, Hubble has a resolution of about 0.05 arcseconds but a field of view of only 0.01 square degrees. James Webb has a resolution of about 0.1 arcseconds but a field of view of only 0.002 square degrees. Euclid can combine both high resolution and large field of view, which makes it ideal for mapping the large-scale structure of the universe. The second picture we see is from the NISB camera, and it shows a patch of sky that contains about 200,000 stars and galaxies. The colors in this picture represent different wavelengths of near-infrared light, with blue being the shortest and red being the longest. The resolution of this picture is about 0.3 arcseconds, which is slightly lower than the VIS picture. This picture is remarkable because it shows the versatility and sensitivity of the NISB camera. It can capture images that are much wider and redder than those taken by previous or current space telescopes, such as Hubble or James Webb. For comparison, Hubble can observe near-infrared light up to 1.6 micrometers in wavelength but not beyond that. James Webb can observe near-infrared light up to 5 micrometers in wavelength but not below that. Euclid can observe near-infrared light from 0.9 to 2 micrometers in wavelength, which covers a wide range of galaxies and stars. These sample pictures from Euclid's cameras are just a glimpse of what this amazing space telescope can do. In the next few years, Euclid will take more pictures like these and use them to study the dark universe in unprecedented detail and accuracy. By doing so, Euclid will help us understand some of the most fundamental mysteries of cosmology, such as how the universe began, how it evolved, and how it will end. Thank you for watching this video, and if you enjoyed it, please like, share, and subscribe to our channel for more videos like this one. And don't forget to check out our previous episode on how Euclid will collaborate with James Webb to explore the universe even further.